So in the last class we saw how we can define the stability of a system or determine the stability of a system using phase portraits. We studied uh, there are there is a focus regarding the singular point. On the derivation of a singular point, you can determine the phase portrait around the singular point. And you have a focus, you have a node, you have a saddle, and you have a vortex. So these can either represent stable systems or unstable systems. Accordingly, you have six different types of phase portraits corresponding to six different locations of the pole. So you can say also whether the system is behaving, uh, whether the system response is overdamped or it is underdamped or it's simply unstable or maybe even marginally stable. Fine. So continuing with the phase portraits, uh, we'll today see how we can determine uh, limit cycles using the phase portraits. Fine. So already we have done an example of a Van der Waals oscillator and we have designed the phase portrait of a Van der Waals oscillator. And from that we defined that limit cycle on a phase portrait basically refers to on a phase portrait it refers to a closed loop or circle, uh, closed to a isolated and closed loop. Fine. So there will be phase trajectories on the phase portrait that will be converging towards the limit cycle, or there may be some phase trajectories that will be diverging from the limit cycle. But on a phase portrait, if you have some closed loop that's isolated, uh, this will refer to a limit cycle. Fine. And limit cycle, as we know, it basically for a nonlinear systems we define limit cycle as the as sustained oscillations of fixed magnitude and fixed frequency. So now we have to define whether a limit cycle is stable or unstable or marginally stable. Uh, so you can have all the three. You can have a stable limit cycle, you can have an unstable limit cycle, or you can have a semi-stable limit cycle. So limit cycle on the phase portrait refers to any isolated closed curve. Now this phase portrait can actually be referring to a stable limit cycle. That means the system will be exhibiting stable properties, or it may be the limit cycle may be referring to an unstable system, or it may be a semi-stable limit cycle. Now what a stable limit cycle looks like is all the phase trajectories in the system will be converging towards this loop. From whatever point you are starting, if the phase trajectories are converging towards the loop and then sustain within this loop, uh, such a limit cycle will be referred to as a stable. Such a system will be actually a stable system. Why? If all the trajectories in the system are actually diverging out of the loop, then this will be referring to an unstable system. If some of the trajectories in the system are diverging, converging towards this loop, and some are basically moving out of this loop, then this system will be referred to as a semi-stable system. Limit cycle, as I have already defined to you, a nonlinear system will exhibit the property of sustained oscillation of fixed magnitude and fixed amplitude without any external disturbance. This system will continue to oscillate. And on a phase portrait, this can be exhibited using an isolated closed curve that that we have already seen in case of a Van der Waals oscillator. We derived the phase portrait of a Van der Waals oscillator, and we saw that uh, the curve will actually tend towards a loop. Fine. Now this loop, this system can still be stable or unstable or semi-stable depending upon whether the phase trajectories in the system are converging towards this loop or they are diverging out of this loop, or they are, some of them are converging and some of them they are diverging. Then it will be a semi-stable limit cycle. Fine. uh,
सर आइसोलेटेड का मतलब समझ में नहीं आया.
क्या समझ में नहीं आया?
सर आइसोलेटेड का मतलब क्या है? Isolated closed curve बोला ना, फिर limit cycle is defined as isolated closed curve. What is isolated?
Whenever you have any system that will exhibit the property of limit cycle, उस case में definitely we are talking about second order systems only in right now, because the phase portrait is limited to second order systems. Those systems will have, will exhibit उनमें प्रॉपर्टी ये होगी कि उनका जो x1 x2 ग्राफ होगा, that will actually refer to a closed curve on the phase portrait. Fine. We have already seen this in case of a Van der Waals oscillator. आप अब किसी भी इनिशियल कंडीशन से स्टार्ट करो, the phase trajectories will start to converge towards this loop and then sustain within this loop. ठीक है, ये इसी लूप में फंस जाएंगे, it will not come out of this loop. या फिर अगर ये इसी लूप में already exist हैं, at some stage they may diverge out of this loop as time t tends to infinity. In case they are sustaining within this loop and all the phase from any initial condition you are starting, the system is tending towards this loop and remains in this loop forever, the system will be said to be stable. In other cases, initially the system might be showing a property of limit cycle और ये इस loop में continuously behave करेगा, but at some point of time it might start diverging out of this loop, and that means this system has become basically unstable, and it will the phase trajectories will start moving out of this loop. ठीक है. In some other cases, some of the phase trajectories may be tending towards this loop, some of the phase trajectories may be diverging out of this loop, depending upon whatever the initial conditions you are taking. That will refer to a semi-stable limit cycle. Limit cycle, since it is an undamped oscillation, जैसे हमने पहले भी किया था, for any undamped system there is a circular graph. Now in case of a limit cycle, this may not be exact circle, but this may be a closed curve. This curve can be isolated from in the phase portrait at any place. This closeness basically indicates the periodic nature. ठीक है, x1 x2 वापस उसी पोजीशन पे पहुंच रहा है. ठीक है, this trajectory has to be closed, and this closed nature basically refers to the periodic nature of the motion of the system. Fine. And while as the isolation here means this system is limited. ठीक है, there will be a certain nature of the cycle that is जिसकी वजह से इसको लिमिट साइकिल्स बोलते हैं. There will be a property for some duration of time. This system will be in this sustained motion. After some time, if you basically apply some external disturbance आएगी system में, या फिर अगर applying an external force, the system will move out of this system, out of this loop, and tend towards infinity or whatever the nature of the system will be, and accordingly you can then decide whether this system is stable or unstable. In short, limit cycle sustained oscillations है, और sustained oscillation phase portrait पे x1 x2 curve will be a closed surface, whether it will be circular in nature or semicircular or whatever, oval shaped, but any closed surface will basically refer to a periodic nature दैट मीन्स x1 x2 वापस उसी पोजीशन पे पहुंच रहा है अगेन एंड अगेन. So that means there are oscillations in the system and they are sustained oscillations. Unless any disturbance occurs in the system, they will continue to remain in that loop. Whether now we have to decide whether this system will be stable or not by applying any kind of, by taking different initial conditions, by applying any kind of external force impulse response. You will decide whether this system will behave stable or whether this system will behave in an unstable manner. For that, then you can track the behavior of other trajectories that are converging or diverging from this uh, loop. Fine. So limit cycle will be stable if all the trajectories within the vicinity of this limit cycle will converge towards it as t tends to infinity. Limit cycle will be unstable if all the trajectories in the vicinity of this limit loop actually will diverge away from it. A sustained closed loop behavior refers to the periodic nature, implies the periodic nature of the system. That means आपका जो ग्राफ है वापस इसी पोजीशन पे आ रहा है. That means in actuality your system is behaving in an oscillatory manner. ठीक है. अब आपकी इनिशियल कंडीशंस क्या होंगी, ये कहाँ से स्टार्ट होगा, किस पोजीशन से स्टार्ट होगा, that will vary, but ultimately it will go into a sustained oscillation, or unless you provide a disturbance it will tend to move away from this oscillatory behavior. Is this clear?
Yes, sir.
So you have been given we'll take up an example and see whether this system uh, has a stable limit cycle and unstable limit cycle or a semi-stable limit cycle. You have x1 dot first case x1 dot is equal to x2 minus x1 square plus x2 square minus 1 x2 dot is equal to minus x1 minus x2 minus x1 minus x2 x1 square plus x2 square minus 1. So if you try to plot x1 versus x2 for this very system, you will see there will be a limit cycle. That means there will be a closed curve in which there will be a closed curve and the system will either remain in that closed curve or actually tend to diverge away from that closed curve. So you have to see whether this system will be stable or unstable. Okay. So we have to see whether the other phase trajectories in the system will converge towards it or diverge away from it. तो उसके लिए हम क्या करेंगे, हम इसको पोलर कोऑर्डिनेट्स में रिप्रेजेंट करेंगे. Polar coordinates, that's r angle theta. So r will be given by under root of x1 square plus x2 square, and theta will be given by tan inverse of x1 x2. Fine. So r is equal to under root of x1 square plus x2 square. Differentiating on both sides, dr by dt is 1 by 2 under root of x1 square plus x2 square into internal differentiation. Internal differentiation of this will be 2x1 x1 dot plus 2x2 x2 dot, which implies dr by dt is equal to 2 common निकाल के this will be x in x1 dot plus x2 dot divided by under root of x1 square plus x2 square, that's actually r. Fine. ऐसे थीटा आपका tan inverse of x2 by x1 है, differentiating on both sides, d theta by dt is equal to differentiation of tan 1 divided by 1 plus x square into internal differentiation x1 SA x2 की differentiation x2 dot minus x2 SA x1 dot. So this implies this is equal to x1 x2 dot minus x2 x1 dot divided by x1 square plus x2 square. तो ये आपका डी बाई डी टी है और ये आपका डी थीटा बाई डी टी है. Fine. So you have been given an example. We want to see whether ये क्वेश्चन वहीं से कि आपका सिस्टम लिमिट साइकिल बिहेवियर दिखाता है एट सर्टन फॉर सर्टन ड्यूरेशन ऑफ टाइम और सर्टन और फॉर इनफाइनाइट ड्यूरेशन ऑफ टाइम, जब तक आपने इस सिस्टम को कोई भी एक्सटर्नल डिस्टर्बेंस नहीं लगा के रखी है. द सिस्टम इज एग्जिबिटिंग द प्रॉपर्टी ऑफ लिमिट साइकिल, दैट मीन्स इट विल ऑसिलेट. You can actually try to plot the response of x1 and x2 with respect to time. You can also plot x1 versus x2, that's the phase portrait of the system, and see whether there is a closed curve on the system or not. ठीक है, on the phase portrait whether there is a closed curve or not. Whether to determine this system is stable or unstable or semi-stable, we'll see how the system response behaves in the polar using the polar coordinates. तो हमने क्या किया, पहले r निकाला, r is under root of x1 square plus x2 square, theta is tan inverse of x2 by x1, differentiating both these terms, dr by dt is this, dx by d theta by dt is this. Now substituting the values of x1 dot and x2 dot here, x1 dot और x2 dot जो आपको दिए हुए हैं, this is equation number 1, equation number 2. So equation number 1, substituting the values of x1 dot and x2 dot, dr by dt is x1 into x1 dot, x1 dot is x2 minus x1, x1 into x1 x2 minus x1 square, x1 square plus x2 minus 1, this is x1 into x1 dot plus x2 into x2 dot, x2 into x2 dot, that is minus x1 x2 minus x1 x2 minus x2 square, x1 square plus x2 square plus minus 1, dr by dt is x1 dot plus x2 dot divided by r, which implies dr by dt is equal to minus x1 square plus x2 square minus 1. ये कॉमन निकाल के अंदर आपको x1 square plus x2 square आएगा divided by r. x1 square plus x2 square is actually r square, that means minus r square plus 1 into r square divided by r which implies minus r square minus 1. Fine. So dr by dt is equal to minus r square minus 1. Let's see d theta by dt.
स्क्रीन नहीं
d
चल रहा है,
theta
आप
by
कुछ लिख रहे
dt
हैं?
is d theta by dt is x1 x2 dot minus x2 x1 dot divided
सर
by
स्क्रीन हैंग हो गया.
Is it visible now? So d theta by dt is x1 x2 dot minus x2 x1 dot divided by x1 square plus x2 square. This is actually r square. ठीक है, इसको हम r square भी लिख सकते हैं.
सर नहीं आया अभी भी.
हाँ,
सर अभी नहीं आया स्क्रीन.
किसी को आ रहा है?
नो सर.
In the first example, we saw the system for any initial condition where r is greater than 1, the velocity is negative, so the the phase trajectory from that initial condition will tend towards the loop, while as any initial condition that was inside the circle, velocity was positive, so the phase trajectory tracked from that initial condition would tend towards the loop again. It would converge, all the trajectories would converge towards the limit cycle, so towards the closed curve rather, so the system was stable. In the second case, for this particular example where we took x1 dot x2 plus x1 and x1 x2 dot minus x1 plus x2, for all the initial conditions that lie outside the circle, for r greater than 1, dr by dt is greater than 0, that means velocity is positive, so your trajectories will move away from the unit circle. For all initial conditions where r is less than 1, dr by dt is negative, that means your trajectories will move away from the limit cycle, so the limit cycle is unstable in this case. Example number 3, you have x1 square, x1 dot sorry is equal to x2 minus x1 r square minus 1 square. Just like the first example, x2 dot is equal to minus x2 minus x1 r square minus 1 square. Fine. यहाँ पे खाली आपका ये एडिशनल स्क्वायर है, ठीक है. So in the first example what we saw, जो हमारा अब हमारा जो डी आर बाई डी टी आएगा डैट विल बी माइनस आर स्क्वायर माइनस 1 स्क्वायर. So for this case dr by dt will eventually come out to be minus r square minus 1 square, and d theta by dt will again be minus 1. So in this case you can see for r equal to 1, sorry, r equal to 1, dr by dt is 0 as expected. For r greater than 1, for all the initial conditions that are outside this unit circle, if you start on this unit circle, you tend to remain in this unit circle for infinite duration of time. If you start from anywhere outside this unit circle, initial condition lies outside this unit circle, outside this loop. For r greater than 1, dr by dt will be for r greater than 1 in this case, dr by dt will be negative. ठीक है, so that means कोई भी पॉइंट इससे बाहर होगा, that will move towards this circle. Fine, जैसे पहले केस में भी था. Now if r is less than 1, what happens to dr by dt in that case? In the first case, अगर ये नेगेटिव था, ये माइनस माइनस पॉजिटिव हो जाता. लेकिन in this case, if this is negative, r square is less than 1, this term becomes negative, this still becomes positive, that means this is still negative. So r less than 1, dr by dt is still negative. That means if there is any initial condition that lies within this closed curve, its velocity is still negative. That means it will still tend towards the origin and not towards the limit cycle, towards the closed curve. So this trajectory is not converging towards the limit cycle, it is diverging away from the limit cycle. So there are initial conditions for this example that are outside the circle that are converging towards the limit cycle, but all other initial conditions that are within the unit circle, they are diverging away from the limit cycle, from the closed curve, and therefore the system is semi-stable. Fine. So if you have any phenomenon, so a phenomenon of limit cycle basically means uh, you have an oscillatory response and your system will tend to remain in oscillatory behavior unless otherwise disturbed, unless otherwise your initial conditions are somewhat different. And now you have an example whether your limit cycle is a stable limit cycle, represents an unstable limit cycle, or a semi-stable limit cycle. For that, you need to understand the behavior of the trajectories that lie in the vicinity of this limit cycle, whether they are converging, diverging, or both converging as well as diverging from the limit cycle. So we have taken this example जिसमें हमने 3 different cases लिए, एक stable system का लिया, दूसरा unstable system का लिया, और तीसरा एक semi-stable system का लिया. In short, limit cycle means there is a oscillation, there are oscillations, sustained oscillation, there is a periodicity, and periodicity on a phase portrait means a circular or you can say a closed curve. ठीक है, it's not necessary to always be a circle, it can be oval shaped, it can be any ellipse, but it will be a closed curve, it will come back to its original location. There will be sustained oscillations of fixed magnitude and fixed period. Fine. So this is about limit cycles and how we can determine limit cycles through the phase portrait. Any question regarding this? Fine.